41st lecture, problem session 10 on tuned amplifiers. The first problem is to design a single tuned amplifier which has the following specifications. F0, the center frequency is 455 kilohertz, the bandwidth is 10 kilohertz, and as I had mentioned, this is a typical IF stage of a radio receiver. The transistor that is to be used has the following specs. GM is 0.04 mho, beta 100, C pi 1000 puff, C mu 10 puff. Now these may be given like this, or you may have been given an FT. If you know FT, then you can calculate C pi, provided C mu is given. C mu has to be given. Then the bias network R sub B, the bias network R1 parallel R2, and the source resistance, it's a current source, the source resistance, they are in parallel, they combine to make a 5K. RL is 500 ohm. In addition, as a matter of practical specification, it is stated that a coil which is to resonate at 455 kilohertz, coils with Q between 10 and 150 are available. Coils with Q between 10 and 150 are available, which means that you cannot assume the inductor to be perfect, which means that the inductor has a series resistance. Is the point clear? If it is not specified, then you take the inductor to be infinite Q, that is its series resistance approximately equal to 0. If this is not specified, if it is specified, then you have no alternative. So this is a fairly practical problem. Let us see how to solve this problem. The circuit that we plan on, it's almost given, everything is given. It is given that this resistance, we call this RS prime, okay, RS parallel RB, we call this as RS prime. This is given as 5K, then you have, you connect the tuned circuit here. It's an L in series with a resistance R. Okay, it's series resistance. We had to use capital R because Q is specified to lie between 10 and 150. That means you have a choice of Q. Let us see what Q we shall choose. Then there is a capacitance which we call C prime. This is not the total capacitance because the transistor reflects a capacitance. So C prime is the externally added capacitance, and as we shall see, this will dominate at 455 kilohertz. C prime dominates over what is reflected by the transistor. The transistor, of course, is a common emitter connection. We have not shown the biasing network, that has been taken care of here, and the load is 500 ohm. This is RL, and this is the current I0 or IL, and this is the input current IS. Okay. This is the circuit that we plan on. Of course, for tuning, you have to keep C prime as a part of it, at least variable. Okay. As you know, air variable capacitors with a range of a few puffs to, what is the maximum? 500 puffs, actually 478 or something. A few puffs to 400, a few puffs to 500 puffs. This is the air variable capacitor. So if this lies within that, you can use an air variable capacitor and tune it. If it lies outside, if it is more than that, then you use a fixed capacitor in parallel with an air variable capacitor. We will see how. But the equivalent circuit now is therefore IS. Then now what are the things that will come in parallel? One of them is, of course, RS prime. Okay. We call, would you allow me to change this to smaller? The reason is that the equivalent resistance I want to call capital R, okay, equivalent resistance that comes in parallel with IS. Allow me to call this small r, then the resistance capital R that will come here would consist of RS prime, which is 5K, then a parallel equivalent of LR, which is RP. What is the value of RP? Omega 0 Q times L. We had derived this. The series RL combination has to be converted to a parallel RL combination, and then the equivalent resistance is this correct? Omega 0 QL. Yes, it is correct. What is Q0? Omega naught L by R. Okay. This parallel, what is the third parameter? R pi. And what is R pi? Beta is given as 100 and GM is 0.04. So this is equal to 2.5 K. Okay. This is the total resistance that comes in parallel. Then the parallel inductance is still L. Then we have, instead of C prime, we shall have a C, where capital C is equal to C prime plus C pi plus C mu 1 plus GMRL. Okay. This is the total capacitance that comes here, and this voltage is V pi. Then we have the GM V pi and RL. This current I0 is the output current. All right. Now the specification says that the bandwidth, obviously one of the specifications is that parallel square root of 1 by square root of LC should be equal to omega 0, whatever is given. But you see, we cannot find out L or C directly, because C involves RL and capital R, that involves, well, capital R does not come into the picture. Okay. Yes.
Why don't we consider the effect of Semi on the output stage?
We don't consider, because this time constant is usually far away from the resonance frequency. C mu is a small quantity, RL is also a small quantity, so this time constant is very small, and therefore its effective frequency is very large. We don't consider that. Okay, so we take the first specification, that is bandwidth, which is equal to twice pi. Look, I am multiplying by 2 pi, multiplied by 10 kilohertz is 10 to the 4. This should be equal to 1 over RC, as we have already found out. All right. Therefore, C, the capacitance that is required, is given by 10 to the minus 4 divided by 2 pi multiplied by 1 by R, and 1 by R is 1 by 5K plus 1 by 2.5K, that is 2500, plus RP, 1 by RP, and 1 by RP is Q0, Q, oh, the series Q, obviously. Okay, RP is equal to Q omega 0 L. Now, I want to find out C. Can I write this as Q divided by omega 0 C? Agree? Let's do that. I don't know Q yet. Q has to be chosen. Divided by omega 0 is 2 pi times 455 times 10 to the 3 C. Is that okay? Is this point clear? Q by omega 0 C. Instead of omega 0 L, I write 1 by omega 0 C, because they have to resonate at omega 0.
So there is 1 by RP. It's 1 by RP.
Yes, I require 1 by RP, because I am making, this is equivalent to 1 by R.
So omega naught C by Q. Omega naught C by Q. Omega naught C.
Oh, you are right. This should be to the power minus 1. Okay. Now is it okay? All right. Now this quantity, you see, we could have solved for C if we knew Q, but let's see what are the limitations on Q. You will see a very interesting thing. If you find C from here in terms of Q, after clearing this mess, the result is as follows: 0.95 times 10 to the minus 8 divided by 1 minus 45.5 divided by Q. That's what you get. In other words, you have to choose a coil whose Q is greater than 45.5. Is that clear? Point clear? Okay. And since it is given that Q can range between 10 and 150, you choose a convenient value. Let's choose Q equal to 100. Let's choose a coil with a Q of 100. Then my C becomes equal to how much? 0.018 microfarad. That's what you get. Pardon me? 0.0181. Will someone tell me? I seem to have made a mistake.
180. Yes, sir. 1.7 into 10 minus 8.
1.7.
1.743 into 10 minus 8.
Okay, so 0.0173. Is that okay?
Yes.
Okay, so many microfarads. Agreed. Therefore, what is C prime then? You require the external capacitance. You see, C prime, C as you know is C prime plus C pi, which is given as 1000, plus C mu, which is given as 10, multiplied by 1000 puff, plus 10 multiplied by 1 plus GMRL, that is 0.04 multiplied by 500, which is approximately C prime plus 1200 puff. Agreed? Now therefore, C prime is C minus 1200 puff, that is 0.0173 minus, let's see, how much is this? 0.012. Is that okay? 10 to the minus 2, so 0.1.
It's 0.001. Yes, sir.
0.0012. Don't make a mistake.
Yes.
Now 0.0012. You see that this capacitance is negligible compared to 0.0173. Nevertheless, the value is 1610, 0.0161 microfarad. This is C prime. And you see that C prime dominates in C. This is desirable. Why? Because if the transistor is replaced, for example, it will have a different C pi and C mu. It should not affect the tuning too badly. And nevertheless, if the transistor is replaced, that variable component of C prime, that will take care of it. You tune it again. That's all. So we have found out C prime, we have found out C. What remains to be found out is L. L is 1 by omega 0 squared C. And since C is 0.0171, was that the fellow? 0.0173, and omega 0 is given 455 kilohertz. This can be calculated. This comes out as 6.9 microhenry. Now let's also calculate what is RP. RP is Q omega 0 L, or Q divided by omega 0 C. If you substitute the values, this comes out approximately as 2K. Why is RP needed to be calculated? Why did we calculate RP? To see if we require an external resistance. No. We have already taken care of this. We don't require an external resistance. To find out the mid-band gain, can you tell me what the gain would be? Let's look at this circuit. Not mid-band, the resonant gain. Okay, the gain at resonance. Let's look at this circuit. What do you think will be the gain at resonance? I0 by Is. Look at this circuit and tell me. Yes? Pardon me?
Parallel combination of
Would it be a minus sign or plus sign to start? Minus sign, because I0 and GMV pi do not agree. And at resonance, you see L and C produce infinite impedance. and therefore V pi would be Is times R, and therefore it's simply minus GMR. That is the current gain. Okay. In order to calculate this, we require the value of R, and therefore we require RP. And therefore R is the parallel combination of 5K, 2.5K and 2K, which is equal to 910 ohms, my calculation, and therefore AI0, the resonant gain, is minus GMR is equal to minus 36.4, and the design is complete. The design is complete. Any question before we go to the next one? Next one would be a little more involved, but let me point out that if an inductance, this inductance 6.9 microhenry is really a very low inductance, and if an inductance with this value cannot be easily made, maybe it occupies too little a space, and your standard ferrite core that is available is longer. Okay, so it would be beneficial to wind a larger coil. Okay, if that is required, you do that and take a tap. But the next question is that of designing a tapped inductor or an auto transformer coupled tuned circuit. The next question, question 2, is the specifications are the same, almost the same. We'll make a slight variation in the transistor. Okay, we still have to design a tuned circuit whose F0 is 455 kilohertz. That is the IF stage of a radio receiver. The bandwidth is still 10 kilohertz, and now the circuit is specified. The circuit is specified to be this. Draw this circuit with me. Is and Rs is found to be 5K, an external capacitance C prime, then a coil whose inductance is 6.9 microhenry, the same as in the previous case, 6.9 microhenry, and let's say the number of turns here is N2. Number of turns is N2. Then you take a tap from here, and what comes in parallel with this is the biasing resistance RB, and it is given that RB is much greater than R pi, and R pi is given as 1K. All right. So RB is shown, but its effect need not be considered. RB may be typically 30 to 40 K, and then you have the transistor, emitter, common emitter transistor, and the load is the same, 500 ohm, and this current is I0. Here R pi is given, and the coil Q is given as 100 at F0, that is at 455 kilohertz. The coil Q is given as 100. C pi is given as 1000 puff. GM, in order that you cannot use all the data of the previous example, GM is changed, 0.1 ohm. RL is given, and C mu is also changed to 4 puff. The question is to design this circuit and to find out the midband gain, AI0. Not midband, now it is resonant gain, center frequency gain. Okay. Now you notice what does the design involve then? All that you have to do now is to find out, let's call this turns ratio as N1. All that is required to be done is to find C prime, the external capacitance that is needed, and the turns ratio N2 is to N1 or N1 is to N2. Okay. For bringing variety into experience, we will call this as A. We will call this as the primary and this is the secondary. Okay. N1 by N2 is equal to A. We will call this as the turns ratio. All that you have to do now is to find out C prime and A. all right. Everything else is given, the coil is given to you. You are only allowed to make a tap. Now, where would you choose the tap? That is the question. And what capacitance would be needed? Because the capacitance here will be reflected into the input circuit, and therefore C prime that is required shall be different. Let us see how to solve this problem. It's a fairly practical problem and fairly involved problem. The equivalent circuit of this would be the following. You can draw this very quickly. 5K, then C prime, then the inductance L, which is 6.9, the tap. What comes across the tap? First is R pi and then a CT. This voltage is V pi, where R pi is given as 1K and CT would be C pi plus C mu 1 plus GM RL. This is equal to 1000 plus 4 puff 1 plus 0.1 multiplied by 500. So, it is approximately 1200 puffs. 1200 puffs. Then you have the GMV pi and RL, and this current is I0. This is the equivalent circuit. And I know everything. Pardon me? RP. Oh, the parallel capacitance. Where would that come? Yes, that's a very good point. It should come in parallel with, okay, this is, I beg your pardon, the inductance is 6.9 microhenry and a Q of 100. So, this is not a pure inductance. If it is to be reduced to a pure inductance, its equivalent parallel resistance at resonance must be reflected and combined with RS. Very good. So, you have to include RP here. RP parallel 5K. No, because it is in this, it is across the total, and therefore the total inductance has to be used. It is R pi and CT which will be reflected into the input circuit by R pi would come as R pi multiplied by, that's right, that is R, no, that's wrong. This is N2. This is, I said, this is why I said I will bring variety into experience so that you are, okay, R pi by S square, and CT would come as S square times CT. Okay. So, let us look at the input circuit now. Equivalent circuit, by reflecting R pi and CT into the input circuit, we have 5K parallel RP, we have a C now, where C is C prime plus 1200 puff multiplied by S squared. Is that okay? The capacitance CT is 1200 puff, that would be multiplied by S squared. That is how it is reflected. This is C. Then you have the inductance L, which is 6.9 microhenry as given, and the resistance would be reflected as R pi divided by S squared. So, it is 1 by S squared kilo. Is that okay? What would this voltage be now? V
pi into A. V pi into A. A into A.
Not into A. Don't make a mistake again and again. This is why I chose N1 by N2 equal to A. It would be V pi by A. Then you have the GM V pi RL I0. Before I go further, can you tell me what would be the center frequency gain AI0? This is not V pi. If it was V pi, then it would have been minus GM times the equivalent resistance here. This is V pi by A, and therefore there should be a factor of multiplication or division.
Multiplication.
So it will be minus A GM R, where capital R is equal to 5K parallel RP parallel 1 by S squared K. Agree? Now let's take the what is RP? RP also we know 6.9 microhenry, omega 0 we know, and we know Q, and therefore it would be the same as in the previous case, it would be 2K. Agreed? Or the only thing that we do not know is 1 by S. What is A? Returns ratio. Okay. So the first thing we find out is from the bandwidth, no, our R is 5K parallel 2K parallel 1 by S squared K, and therefore 1 by R is equal to 1 by 5000. I will require this in the calculation of bandwidth. In the calculation of C, we will see plus 1 by 2000 plus S squared. S squared
Into
down,
1000.
huh?
Into 1000.
Divided by 1000 or multiplied by 1000? Wonderful. So many moles. Okay, and this comes out as 10 to the minus 4, 7 plus 10 S squared. So A is the quantity. A is a quantity to be found out. This can be found out from the bandwidth specification. But before we do the bandwidth specification as you know, B is equal to 1 over RC, B in radians per second. We require a C. Since we know L, therefore we can find out C. The required capacitance C is 1 by omega naught squared L, and that is equal to 1 by 6.9 microhenry okay, 6.9 microhenry multiplied by 2 pi times 455 times 10 to the 3 whole squared, and this comes out as 0.017. It would come out exactly as 0.0173, exactly as in the previous case, isn't it? 0.0173 microfarad. So many farads, so many microfarad. And C, as you know, it should come out to be the same. Okay, and C, as you know, is C prime plus, did we find it out? 1200 puff multiplied by S squared. Now that is, you look at now a designer's common sense. C prime plus S squared multiplied by 1200 puff means how many microfarads? 0.0012 microfarad is equal to 0.0173 microfarad. Now the designer comes into effect. A is less than 1. Isn't it right? A is N1 by N2, and therefore this quantity will be very small compared to the right hand side, and therefore C prime is approximately equal to 0.0173 microfarad. That is approximately equal to C. Agreed? Now we can go and find out from the bandwidth specification the turns ratio. The bandwidth specification is that 2 pi times 10 to the minus 4 would be equal to 1 by RC, that is 1 by 0.0 17 multiplied by 10 to the minus 6, that is C 173. Okay, 1 by C, then 1 by R. 1 by R we have already found out to be 10 to the minus 4 times 7 plus 10 S squared. All right, which has now to be crammed up for finding out the value of A, and S squared comes out approximately as 0.4, so that A is equal to 0.63. A is equal to 0.63, which means that if the original one is 10 turns, this should be 6.3 turns, N1 should be 6.3 turns. Okay, and the center frequency gain, which was minus A GMR. Yes.
So the unit of 1 by RC is hertz. How can you equate to 2.10 to the minus 4? Should be 2.10 to the power 4.
1 by RC is hard.
No, 1 by RC is time bound.
Okay, 1 by RC is radians per second. Yeah. You see, SRC is a dimensionless quantity, and S is in radians per second, and therefore RC must be inverse of radians per second. This is okay. Do not make a mistake. You see, if I have a simple low pass filter, where is the cutoff frequency? 1 by 2 pi RC. This is in radians per second. Oh. What mistake did I make?
Minus sign.
It should be plus. I am sorry about it. It should be plus. Otherwise everything goes wrong. Okay. The final problem of, is there any question on this? You have to do this very carefully. What is required to be done must be very clear to you. Your aim is to find C prime and A. These are the two quantities, and these are interlinked with each other. You see, there was a point when we were absolutely at a loss to understand what should be done. Suppose we did not ignore this, then we had to have an equation which contains both C prime and S squared, only one equation. You could not solve for both, but this common sense that A is less than 1 has helped us to solve the problem. This is how a designer comes into application of his common sense. The final problem is that of a synchronously tuned amplifier, and we shall assume that we have only two stages of synchronous tuning. In other words, we have two resonant circuits which resonate at the same frequency and their bandwidths are the same. And one of these very simple ways of making this is to have two transistors. IS, you have, for simplicity, let us assume that perfect coils are available. If they are not, then you have to convert them into L in parallel with RP. Okay? So let's assume that we have perfect coils like this, or coils whose resistance has been taken into account in, we'll introduce a resistance R1 here, okay, in R1. Then you have, this is one of the tuned circuits. The other tuned circuit comes in the load or in the collector circuit of this transistor, and for some reasons, for biasing and other considerations, this resistance is 10K. For biasing this transistor, this resistance is 10K. Then you have a capacitance C2 and inductance L2. Once again, we assume that the parallel resistance of L2 has been absorbed in 10K. All right. And then you have a second transistor whose load is 100 ohm, and this is the output. For variety into experience, we assume that the output is the voltage. A question that could be asked at this stage is, well, why didn't you take the output from here itself. From here itself. Why didn't you take the output from here itself? The condition of the problem says you could not. Why? Pardon me? Because the load is specified as very low resistance, 100 ohm. Agreed? If you put 100 ohm here, all this tuning, not tuning, the bandwidth, that goes absolutely away. Okay? The bandwidth becomes very, very large. In other words, if the tuned circuit becomes a flat tuned circuit like this. Okay? So you do require a buffer. Okay? Now let's see how to solve this problem. The equivalent circuit, if we draw, the specifications are as follows. Now again, to bring variety into experience, the specifications are that Ft is given 10 to the 3 megahertz. Okay, Ft is given, and the bandwidth, well, it is required to resonate at 100 kilohertz, and the overall bandwidth B is required to be 2 kilohertz. Overall bandwidth is required to be 2 kilohertz. That's it. The transistors that are used have Ft equal to 10 to the 3 megahertz, beta equal to 100 for both of them, R pi is 1K, in other words both have the same GM, okay. R pi is 1K. What else do you need? What else do you need? C mu is given as 2 puff, and it is said that Rx tends to 0 and R0 tends to infinity. Alright, this is the specification of the problem. You have to find out what are the things to be found out here. This capacitance C1, the inductance L1, we don't know what this resistance is, we have to find R1, then you have to find C2, L2. That's all?
Yes.
Gain, okay. That of course, that also. Can we write the expression for this gain at the center frequency, AI0? Can we write an expression right by looking at it? Can you do that? For the last stage, without drawing equivalent circuit. For the last stage, it is minus GM times 100. Okay. Then for the second stage, minus GM times 10K parallel R pi. 1K. That's right. Okay. Then for the first stage, yeah.
There are 2 stages here. Only 2.
For the input circuit,
R1 parallel R pi.
V pi over Is. That is the gain now.
Okay.
So that would be R1 parallel
R pi.
R pi. Absolutely wonderful. We can write this by inspection, and therefore if you know GM, you can find out GM. All that you have to find out to find the center frequency gain is to find R1. That's the only thing that is unknown. All right, and the equations. Well, let me draw the equivalent circuit. Then the equations will be clear. What I will have is Is parallel C1 L1.
Excuse me, Sergeant, one question.
Yeah.
So this AI0 is a ratio between what and what? V0 by Is?
That's right. Because our output is V0 and input is Is.
So, but, okay.
It has the dimension of, look at it, it has the dimension of resistance. This is dimensionless, so it's a dimension of impedance. It has to be V0 by Is. Okay. C1 L1, then you have the parallel combination of R1 and R pi. Agreed? From the first transistor. And you have the capacitance as, actually this capacitance, okay, since we have drawn it separately, this is CT1, which is equal to C pi plus C mu 1 plus GM times 10K parallel R pi. Okay. Then this is V pi 1. Then you have GM V pi 1. This resistance should be 10K parallel R pi, agree? 10K parallel R pi. Then you have, what would be this resistance? C2 plus, what shall be reflected? C pi plus C mu 1 plus Gm multiplied by 100. That is correct. This is the total capacitance. And then you have L2. Of course, that has to be there. And this voltage is V pi 2. And finally you shall have Gm V pi 2 and in parallel with RL. This voltage is V0. Alright, I couldn't find space here, so I brought it down. Is this okay? Or have I made a mistake? Don't be too sure. I can make a mistake. I shall call this as, what shall I call it? C2 prime, let's say. CT2. Well, I didn't want to use that because I had used this CT1 here. This is CT2. Okay, and I will call C1 plus CT1 as C1 prime. That is the total capacitance here. Then I have 1, 2, 3, 4 equations. What are these equations? Mind you, it is synchronous tuning. Therefore, the equations are omega 0 squared equal to 1 by L1 C1 prime. It should be the same as 1 by L2 C2 prime. This gives me how many equations? 2. And the other one is the bandwidth equation. Now there comes the question, what bandwidth should you use? The overall bandwidth is required to be 2 kilohertz. So what is the individual bandwidth? B1. How do you know? Synchronously tuned, so the bandwidth shall shrink. That shrinkage factor you must take into account. It should be the overall bandwidth divided by obviously the single stage bandwidth has to be larger than the overall bandwidth. So you divide by square 2 to the power half minus 1. This you have to find out, and this is given as 2 kilohertz. So this is 2 pi multiplied by 2 multiplied by 10 to the 3. Is the point clear? You might falter here. If you use a 2 kilohertz, then your calculations will go wrong. This should be equal to 1 by 1 by C1 prime and the total resistance. Total resistance is R1 parallel R pi. It should also be equal to 1 by C2 prime multiplied by what? 10K parallel R pi. How many equations do you get here? 2. So you have 4 equations. What are the things you have to find out? L1, L2, C1, C2, what else? And R1. These are the 5 things you have to find out. So you have 4 equations, so one of them you can choose at your sweet will. You would normally like L1 and L2 to be equal, because this is the problem point. Winding an inductance of a specified value is a problem. So if you have wound it once, then you know exactly how many turns you have to use. So normally you would choose L1 equal to L2. That constrains you to 4 equations, okay, because you have made one choice, and the rest can be calculated. More on Monday.